Good morning and welcome to today's lecture in Parasystems with the topic 13 Dwarfs of HPC. So, a short outline. We're going to talk about, well, the 13 Dwarfs of HPC. The idea of this topic is that so far we talked about low-level categories of applications like task parallelism and data parallelism, but we also discussed blocking and non-blocking communication, synchronous send modes, and so on. All of these things are fairly low level. And back in the early days, people thought about categorizing applications in more high-level categories that allow you to reason about, okay, this is an application of type A, this is application of type B, so probably this is hardware where it will run good, or this is hardware where it will run bad or badly. So we're going to discuss some of these categories today, and afterwards we're going to have a short session of Tales from the Proseminar, where first we're going to talk about Daniel's weird integer problem. Daniel is a student of last semester's course or last year's course, who had a very funny problem, which was a very funny problem. And afterwards we're going to discuss the difference between G++ and GCC compilation with a code excerpt from yesterday's exercises. So, again, short motivation, why do we talk about this? The problem is, I already said, we discussed concepts that relate to the MPI API. We discussed concepts such as load imbalance or task parallelism, and all of these things are pretty low level as it is. It doesn't mean to say that a program is memory bound, a program is dealing with a lot of pointers, or a program has a very structured approach of solving a problem or a very unstructured approach of solving a problem. However, it would also be useful to recognize these higher level classes of applications in order to reason about what would be ideal hardware for them, or what kind of optimizations would I apply to that. And this lecture should provide you with the most prominent HPC classes that are out there, that everybody sort of agrees on, that these are classes which could be used to categorize HPC applications. This list is by no means exhaustive, so you might come up with additional classes, you might come up with a different way of classifying them. This is just one way of looking at the entire landscape of HPC applications. And many applications that you encounter and many applications that we dealt with so far actually fit these categories. So, how were they defined? Well, people try to group applications by similarity in terms of what they compute, how they compute, what are their communication patterns, what are their data structures. And I linked here a PDF of one of the first publications that talks about this and tries to provide a sort of holistic view on the entire thing. In case anybody's interested, you can read this. It's quite a nice paper. It's a little bit old, but it holds nevertheless. Important is to say that these dwarfs are purely algorithmic and implementation independent. So there's nothing in there that talks about, okay, this is good for MPI or this is bad for OpenMP or something. This is really about the structure of the program, the structure of the algorithm, what data structures should look like or should not look like. By no means are they trying to prescribe you with a certain programming model that should be followed or a certain programming language that should be used for implementing these problems. The idea is rather to have cross-platform reasoning in order to allow you to say, okay, this kind of programming model might work well for this kind of problem, and it might work less good or less well for another kind of problem. And it doesn't tell you specifically what kind of hardware or what instructions had to use or anything like that. It's not as specific, because it should be high level, right? We're talking about communication patterns, we're talking about network topologies, communication intensity, and so on, stuff like that. And whether you use MPI or TCP, low-level TCP sockets or whatever you want to use, this is up to you. And these dwarfs are used to kick off innovation in all of these aspects. So whenever people try to come up with a new programming model, with a new hardware platform, accelerators or whatever, they usually select among these classes of programs in order to determine how well is their system suited for computing this kind of problem. So they are sort of generally agreed upon benchmarks for the HPC landscape. Now, they are structured sort of in two groups: the 7 original dwarfs of HPC and the 6 additional ones that were added on later to the fact. first we're going to discuss the 7 original dwarfs, which are dense linear algebra, sparse linear algebra, then spectral methods and n-body methods, structured grids and unstructured grids, and then Monte Carlo methods. And some of those you have already heard. For example, the first one, dense linear algebra, is basically matrix multiplication, or matrix multiplication rather is a type of dense linear algebra problem. And you heard about this in the first MPI lecture where I showed you source code for matrix multiplication. And we are probably gonna implement this in the Proseminar at some point also with optimizations. Next, we talked about particle in cell codes, for example, and you currently, for your current assignment, have to do an n-body implementation. So that's another dwarf. Then we did the heat stencil, which is a type of a structured grid, and we did Monte Carlo pi, which, oh surprise, is a Monte Carlo method. So you already heard or talked about 4 of these 7 methods, and we're going to go into a little bit more detail about all of them, and we're going to discuss also the ones you have not heard about yet. And afterwards we're going to move to the additional dwarfs that sort of diverge from these problems, because these all try to address something that you can find in real-world physics mostly. They're used for physical simulation of physical processes. And the dwarfs that came afterwards deal more with theoretical problems. Okay, so first one, dense linear algebra. So what does dense linear algebra look like? What are the characteristics? And for each of those dwarfs, we're going to first have a short description. What does this look like? What could be an example, so you actually know what these things look like? What's like a real-world thing that you can relate to the name that I put up on the slide? And afterwards, we're going to discuss what are the characteristics of this code, and afterwards, we're going to discuss what are the optimization possibilities of this kind of problem. And for each dwarf, we're going to go through first describing what it is, describing its characteristics, and describing its optimization. So for dense linear algebra, well, data is stored in densely populated arrays, vectors, or matrices, usually in an uncompressed way, so directly as you have the data available. You might access it via strides. Often it's just a unit stride, which means you just access every element after the other. And on the right side, for example, you have a visualization, which is matrix multiplication, which is one of the most prominent examples. But it's basically everything out there that deals with linear algebra. So not only matrix mul, but also LU decomposition. So trying to arrive at the triangular representation of a set of equations or something. Then Gauss-Seidel solvers, Jacobi solvers, and stuff like that. So they all are sort of in this corner of linear algebra. Important here is to know that these are really rarely done manually. So there's a ton of libraries out there that you can use for doing this kind of linear algebra problem, especially matrix multiplication, but not only. There's the entire Eigen library that tries to provide you with means of speeding up this computation. And as I keep saying, don't try to reinvent the wheel. So if you have high-level libraries available that help you with these kinds of problems, use them until you figure out that they do not fit your use case, or they are too slow for your special architecture or something, and only then switch to your own implementation. Don't try to write a library that provides matrix multiplication functions, because there are already 15 out there that probably outperform you unless you invest 3 years of research into the topic. So you shouldn't do this. Now, what are the characteristics of dense linear algebra? Well, naive implementations are usually memory bound. Remember, we have the memory wall, which means that the speed, both in latency and bandwidth, of memory or memory links does not grow or does not increase as fast as computational power. CPUs, the computational power of CPUs grows much faster than the speed of the memory. So people tried to add caches and prefetching to the hardware, but this only gets you so far. So even with all those special features, the first, most simplest implementation you can come up with of linear algebra is really often memory bound. On the right side, you see an example what this kind of, for example, matrix multiplication could look like in code. And the data structure of this kind of problem seems rather easy, right? Because you have just, in this case, two-dimensional arrays where you have data lying contiguously in main memory. And depending on your index order, you can access them the right way by having the fastest changing index being the last one, or you can't do it all the time, like in this example, where sometimes the fastest changing index, as for the B vector in this case, is not the last index, but that's just how matrix multiplication works, right? And this is why I'm stressing that the data structure here is very simple, but it's really significant because these kind of strides often allow or prevent proper use of caches, or they allow or prevent proper use of vectorization, like SIMD, for example. So the B vector, for example, you access every element with a certain stride of n, and this will make it really hard to do proper vectorization unless you have really sophisticated SIMD functions available, as I've shown you on the bottom right, which is AVX, I think, even code that is pumped out by the compiler if you enable vectorization for a code that you see on the top right. These kind of issues like strides, or rather the column versus row major access, so fastest and slowest changing index and so on, they affect these things because vector loading is complicated. We will have a lecture about that later on. And this also affects cache efficiency. We talked about that yesterday also a little bit. And these linear algebra problems are basically still the default measure for performance in HPC, right? So if you check the top 500 that I've mentioned a few times already, and you want to check how fast is every machine, and what performance, what petaflops can I get out of my system, what exaflops can I get out of my system, then HPL is one of the main measures, which is basically just a high-performance linear algebra solving benchmark. That's everything they do, a ton of linear algebra. And nowadays, we start to move away a little bit from only having linear algebra problems, but we start to move towards problems that are sparse, which will be in the next dwarf we're going to talk about, and other things. So people try to sort of move towards having a more diverse set of benchmarks. So I included as an example HPCG, which is a conjugate gradient benchmark, which diverges from this dense prospect and moves more towards sparse matrices because they appear in, I don't know, Google's PageRank algorithm, or potentially machine learning and so on. And you don't want to benchmark your systems with one kind of benchmark, with one category, and then actually use the system for another category of programs and figure out that it's much too slow for them because your benchmark was wrong, right? So that doesn't help. Nevertheless, what are the kind of optimizations that we can apply to linear algebra? And we already talked a little bit about this yesterday. The first thing you could do, which is also shown on the right side of the slide, is loop blocking or loop tiling. So you don't only work on single elements, which would lead you to iterating through a matrix row by row or column by column, especially if you need adjacent elements that are not in the same row or not in the same column. Like for matrix multiplication, it will happen at some point because one matrix you access one way, the other matrix you access the other way. For the heat stencil, we've seen that this is an issue. Heat stencil is not really linear algebra, but the same optimization still applies. And what you can do in that case is the code example that you see on the right, which is another set of loops that basically sets additional boundaries. So we have a loop II and JJ, and these two loops loop over the entire domain, and their iterators are increased with a certain block size. So IB and JB here are not 1, but they are rather 2 or 16 or 32 or something. And then the innermost loops do not iterate over the entire domain, but instead only iterate over the current block. So we move from II to II plus IB, for example, which is the current block size. So that would be, for example, tile 33 up to, or the 32 rather, up to 63, for example. And by doing that, we can exploit locality and the cache. So we try to, and I already explained this yesterday a little bit, we try to work on a single block of data as long as possible and load data into the cache only when we need it. And we don't try to iteratively keep loading, for example, for the 2D heat stencil, load neighboring cells into the cache that we only need once now and we need them again in, I don't know, 500 iterations. Then we're loading the same data twice into the cache. We could rather load the data once and then try to compute a lot of neighboring cells with this one cell that we already loaded into the cache. And once we're done with this information, let's evict it from the cache and load the next tile. And this can really speed up your program. We're going to try to explore this a little bit later on in the Proseminar. And this is only one of so-called higher order transformations, which are, for example, loop transformations. So you could also do loop unrolling, where you try to not do all the iterations with a single line of loop body in the loop, but rather we try to change the loop so that we don't take single step iterations, but we take steps as a factor of 8, for example. So instead of I plus equals 1, we write I plus equals 8, and we have the body of the loop replicated 8 times, which will help you because you have fewer branch evaluations in your CPU and can give you a little bit of a speed up to maybe 20% or something. So that's one thing you could do, higher order transformations. The other thing you can do is vectorization, which might entail some other modifications, like you would need to transpose a matrix in order to not have strided axes, for example. But then also with vectorization, you could get a lot out of this code, assuming, as I said yesterday, that you're no longer memory bound. If you're memory bound, vectorization is not going to help you, because vectorization is something that speeds up the computational power of the CPU. It doesn't speed up memory access. If you're memory bound, no help there. The other thing, or the last thing that's a suggestion on the slide here, is using hardware-specific instructions, like, for example, fused, multiply, and add instructions. Which every compiler will be using nowadays, and their main purpose is not so much as speeding up performance, but also to allow less rounding errors by internally computing with, for example, 80 bits, although you're only working on 64-bit double values, but only the final result of your multiply and add operation will be rounded, and not the intermediate result after multiplying. Then you add the value and then you round again. That it will introduce additional errors in floating point numbers. So FMAs, usually that's why they call fused multiply and add. You do the multiplication and you do it with 80 bits precision or something, then you do addition and then you round to 64 bits. But by offering this as a single instruction, it's also a little bit faster compared to doing 2 separate instructions. Okay, so this is everything about linear algebra. If at some point you have any questions, just stop me in between. The other side of the curtain now is that we do not only have dense data, we can also have sparse data, as you see illustrated on the right. We have a matrix with a lot of elements, but very few of them actually hold data that is not 0, for example. So people also call this sparsely populated, for example. It doesn't even have to be a 2D matrix. It could be a vector. It could be, I don't know, a 7-dimensional matrix, depending on what your problem is. And really the defining property is that, first of all, the vast majority of the data is 0 and doesn't need to be stored. We saw a sort of variant of this yesterday, where we had the data that was not 0 densely populated in a specific region of our domain. But this is a very, very special corner case. Usually when we talk about sparse linear algebra, it looks more like this, that, for example, all the elements on the diagonal are not 0, or just some selected elements throughout the entire matrix are not 0. And here it's more difficult to optimize using the techniques we discussed yesterday. In order to get around this, data is usually stored in a compressed format. We're going to discuss this on the next slide. And you often access data indirectly. So you do not store the full matrix because you will be storing a lot of 0 data, which is not useful. If you store it on disk, you could just compress it with a gzip, 7-zip, or LZMA, whatever algorithm you have out there. Usually people rather try to find a different addressing scheme that actually identifies all the points that are not 0 and the rest of the points you simply ignore. Examples for these kind of problems are conjugate gradient, as I mentioned before, or Google's PageRank algorithm, where, for example, you try to match which websites are linking to what other websites. So you could imagine having a matrix where in both the X and the Y diagonal you mark data where one website links to another website. So as soon as you have a point between some I and J, if it's symmetric, which this matrix is, that means that there's a link from I to J, or there's a link from J to I, for example. And this is how Google tries to rank websites in its search results. And if you do that, for example, this will be huge. Just count the number of websites that Google knows about, and this will be the length of one dimension of your matrix, which is extreme. It's probably millions or billions. So yeah, and data mining is also a very important thing, where we try to gain sort of insight into lots of measurements out there, where we only have select data points and not a full view of the entire picture. So what are the characteristics? Well, for sparse linear algebra, it can be computationally bound, it can be memory bound. This really depends on the sparsity of the data, depends on how you represent the data, and it depends on your algorithm. Most of the time, again, naive implementations are usually memory limited, but this really depends on your actual use case and where the data is located in your data structure. There are different data structures available for this. For example, there's the simple coordinate scheme, which is also abbreviated with COO for coordinate, also called triplet format, or it's simply just a pair of 3 entries, actually a triple, with the coordinate I and j and the value at these coordinates. Very simple. You could implement this in different ways, because you might think, okay, how can I change the data structure? Philip keeps telling me that there are so many different ways of doing this. Very simple, take the difference between arrays of structs and structs of arrays, which is a pretty important optimization when you work with compilers or you try to optimize for vectorization. The code on the right shows you the difference between these two implementation styles. So on the top, we basically have an array of structs. So we have a single element, sparse element, which is a struct with an integer I and an integer j, which are the coordinates. So where is this element? And a double data type with its value. And we can then simply create an array of a certain size, for example, of type sparse element, and we call this sparse matrix, for example. And if we want to set the first coordinate, so that the coordinate of the first element to 0, we access the element at position 0 of our array. We want to access the coordinate I of this element, and we set it to 0. Right. The problem with that approach is, assume now you're interested in all rows or all columns of your data where you have data. So you need to iterate through your array, and you need to read I, then skip over j and value, read the next I, again skip over 4 bytes and a bytes, and again read I. And this is strided access. This is not contiguous in memory, right? And depending on what you're doing with the data, this might be very bad for performance. So what you could do instead is turn things around and simply have a single struct where you have 3 arrays inside. You have an array with all I coordinates, you have an array with all j coordinates, and you have an array with all the double values that you're interested in. You create your array, your entire data structure, by simply creating one element of this struct, because it already holds all the arrays. And then you say, of my data structure, I want to access all the coordinates for I. And of all I coordinates, I'm interested in the first one, and that one I'm setting to 0. If you now have an algorithm that works on all rows or all columns, for example, only working on the coordinates, or simply working on all the data, I simply want to count all the elements that have a certain value or are in between a certain range or something, you can simply iterate through contiguous data. But then again, this really depends on the type of algorithm you run on your data structure. And this shows that people, for example, in algorithms and data structures, we discuss different sorting algorithms and stuff like that in the bachelor, right? And people often focus too much on algorithms and how to work with already existing data structures. And very often they do not consider changing overall the data structure into something that would be much smarter and much more suited to whatever they want to do. They only think about changing the algorithm, but not how the data is represented. And also important, consider that this data doesn't necessarily have to be sorted. So the order of the elements in your arrays, whether you choose one or the other representation here, is completely arbitrary. So it could be randomly sorted, because you're storing the indices separately. The downside is with this approach that you're using quite a lot of data. So people still, for the coordinate scheme, people thought about, is there any smarter way of doing this in order to further reduce the memory footprint, and in order to get less stringent on memory bandwidth and more computationally bound, where we have additional means of improving performance. So one way of doing this is compressed row storage, which needs less memory. What you do is you have 2 arrays of size n, where n is the number of elements that we want to store. One array holds a at ij, which is up here. That's simply all the values, all the non-zero values, actually in this case also included 0 value, all the values that we want to store. And the other array simply holds IDs of columns. So these are columns where this data resides. And then we have a third array, and in this third array we store starting indices of our array j. So how does this work? You already see with the orange colored numbers here that these are the same, right? First we have element 2 and -1, which are the same up here. then we have 3, -1, 2, 3, -1, 2. So this array really just represents the numbers we stored here. And then for each of those, we store the column of J where this element resides. So 2 is in column 0, -1 is in column 1 of J, then 3 again is in column 0, and so on. And then we have our starting array I, where every entry represents a row. So this would be the first, this would be index I0, this would be index I1, I2, and I3, and they point to a starting index in J. And then you sort of try to get this compressed row storage where you tell your algorithm or your system, this is the starting index of I and J. I have that many elements. Once this ends, I move to the next bunch of elements, then I move to the next bunch of elements, and so on. And the advantage of this approach is that the memory footprint is much smaller because you only need twice the sample size or the element size for your arrays A, where you store the actual data, and for J, because for every element you save the column, and then only m+1, which are the entries actually in I that you have. And this is less memory compared to 3 times n, which you would get if you use coordinate storage. And the efficiency of this approach really depends on how your data is structured. So if you try to use something like that for a dense matrix where you have almost every element filled in with values that are not 0 or values that you're interested in, then obviously this is not going to help you, and accessing this is more cumbersome than just using plain indices. So you really need sparse data for that to work. In the meantime, I have a question coming from Daniel. Wouldn't that be the same as having sparse matrix T consisting of sparse matrix size while being more maintainable? Never mind. Okay, yeah. So Daniel asked a question, and apparently he figured out that he had a wrong line of thought. So yeah, never mind. Now for this approach, there are also variants. You can do this differently. You could also, instead of a row major variant, you could use a column major variant, which is called CCS, of course. You could try to store small blocks, for example. So instead of doing something like this, you could just select, I have blocks of 4 by 4 elements, if you know that your data is usually grouped at certain locations, and then you store, for example, full blocks, but only selected blocks in your entire domain. And inside a block, you fill every element, but you only have, say, 32 elements overall in your matrix that consists of millions of elements. And this also improves SIMDiness, because then you sort of have dense data inside a sparse structure by only selecting various regions. Depends on what your data looks like. Or you could have compressed diagonal storage, which would simply assume that you know that you always have elements only on the diagonal, or the diagonal +1, -1, for example. If this is always the case and you're not interested in anything else, then just, for example, store this data contiguously by first storing -1, 2, 3, 2, 1, for example, the first diagonal. Then you go for the main diagonal, and then you go for the third diagonal. And store this contiguously, assuming that you need to access them in this order, for example, or also store them just row-wise, as we did here also with the CRS system. If you know that you are never going to have any element besides these 3 diagonals. Use this domain-specific knowledge, but be sure that whatever input data you get, whatever use case you need to work with, it's only going to be this use case and nothing else. Otherwise, your program won't work. Now, what additional dwarfs are there? So we also have spectral methods, which are sort of strange if you've never heard of them or thought about this stuff. They deal with data in the frequency domain, not in time or space. So in order to show you what this actually means, what this looks like, on the right side you have a simple curve that shows a signal in amplitude, so going up and down. And if you know a little bit about frequencies, you see that we have various frequencies in this signal, because we have very few peaks that are very high, and we have more peaks that are sort of smaller. And if you transform something like this into the frequency domain, where we try to see what frequencies we have and how intensely they occur, then we get a graph that looks like this, for example, where we see we have 5 frequencies in this signal of varying intensity. And the thing that makes these kind of spectral methods difficult to work with is that they usually consists of lots of stages that deal with both local and global communication, which makes it difficult to optimize those because global communication is always expensive. An example for these kind of programs is FFT, the fast Fourier transform, which you might have heard. And for those of you who don't know what this is or what it does is, it's used in lots of audio and video signal processing. So take, for example, some of you might notice digital photo cameras that are sort of cheap or old, and they are bad at focusing. You might have noticed that when you try to take a picture and your camera on your cell phone, for example, is trying to focus, the picture, the image is not sharp. Also in a video, for example, it's not sharp, and it's not immediately progressing to the right point where you have the full sharpness of the picture, but it's searching, and sometimes it's searching beyond the point where the photo is sharp or the video, and then it goes back to the sharpest point. It's sort of overreaching and then going back. This is called focus hunting in photography, and this is exactly caused by something like this. The camera has a chip that is doing this fast Fourier transform or some form of it and trying to derive a frequency picture sort of your photo that you want to take, and is searching with the focus, computing the frequency, and once it reached a setting where you get the maximum frequency, it knows the picture is most sharp, so to speak, and that's where it stops. And because contrast autofocus doesn't know the exact distance, it's not really measuring, it's just checking when is the picture the sharpest, it actually needs to move beyond this peak in order to know, okay, that was the highest point, now it's getting worse, I need to move back now. Because for every sharpness point, contrast-based autofocus doesn't know that this is the maximum. It needs to move beyond that. And if you have a better photo camera, like a DSLR, for example, or a video camera, or a modern cell phone, or a more expensive cell phone, they actually try to do measurements in terms of distance in order to find the exact point where it needs to focus. So, long explanation, but some people get confused by these spectral methods because they don't know what it actually means, what it does, and I hope this explanation helps a little bit. Anyway, what are the characteristics? So usually these look like butterfly patterns in terms of communication or data exchange, which are usually just multiple stages of multiply and add. And on the right, I try to visualize this. And this sort of represents of what's going on, because if you think about how to find frequencies in a photo, for example, you need to have lots of local communication to find high frequencies, and lots of global communication in order to find low frequencies, or to find high frequencies that exist over the entire image, over the entire physical domain of your image. So that's why you need to compare lots of data with lots of other data that is far away from you. And this really often limits you in terms of latency, because you have lots of all-to-all communication going on. And the funny thing about these methods is that they often resemble structure or unstructured grids, which we will discuss afterwards, after transforming the data to the frequency domain. So first you have everything in time or space domain, which is your picture, for example. You have the spatial domains X and Y, and maybe you have the time domain by having individual frames. And then you transform this into the frequency domain, and then whatever algorithm you run on the frequency domain is like a heat stencil, for example, that we worked with. It could be a low pass filter or a high pass filter or something. And this is why the main optimization that you can do in the spectral methods is really to optimize this transformation into the frequency domain, because whatever comes afterwards fits another dwarf that we're going to talk about in a few minutes, and has sort of been well researched. And it's really about transposing and doing this FFT really efficiently. That's why lots of research has been done in this topic for decades. The scalability of these methods is severely restricted because of these latency issues, as I told you, because of these global communication things, these all-to-all exchanges. And remember, we're not talking about MPI specifics here. It's not that I'm always considering an all-reduce or something. All-to-all just means that we need to exchange data between most points in our physical domain or our frequency domain. We're not talking about that this relies on message passing. This could also be implemented with OpenMP, for example. But it still gives you an idea that whatever hardware you want to run spectral methods on should be really fast or equally fast. Doesn't matter which part of the hardware is communicating with which other part of the hardware. And if your hardware is highly segregated, for example, where you have fast communication between adjacent cores and extremely slow communication between cores that are far apart, this might not be suitable for spectral methods. But then again, this topic is actually researched a lot still these days, and a lot of the research is going on not in computer science, but actually in math, in order to come up with algorithms that work better. Then n-body methods. We already talked about these a little bit in our lecture about domain decomposition and load balancing. So we're going to go through this rather quickly. They just model interactions between moving points that are discrete and just sort of map physical properties that actually can move, as opposed to our stencil example where we have a fixed grid where points do not move, just the properties on these points, but not their location. They often require dynamic data structures, so you might need to keep vectors where you can put particles in or take particles out, for example. The spatial locality can vary because you have areas with lots of particles or fewer particles, and all of this affects load balance. You need to be able to move data, and this induces some data access cost, because if you implement n-body with message passing, for example, you actually need to send particles over the network, and this of course is expensive. And these kind of applications are used for galaxy collision simulations, for example, for molecular dynamics, where we try to see how molecules in a solution are behaving, or for protein folding, for example. So there are studies that show that certain diseases are caused by proteins that we have in our bodies all the time anyway, but these proteins can sort of fold together in a sort of energy minimizing state. They are like magnets that try to pull together in a very, very compact form, and there are two local minima of lowest energy, so you have the protein folding one way or the other way, and both are sort of stable. So once the protein is in this form or the other form, it will not change anymore. One of these shapes is perfectly fine, the other shape is causing a disease, like Alzheimer's, for example. And people are trying to research how this is possible, and n-body methods are sort of in the same class of trying to do this folding and trying to arrive at this folding. If you're interested in doing some of these things yourself or having software run on your computer, let me know. There's the Boink project, which allows you to give up computing time in order to participate in computing these problems worldwide. I showed you the SETI at home example already in the first lecture, which tries to find extraterrestrial intelligence with signals from the Arecibo telescope, which unfortunately will be dismantled apparently because it's damaged and can't be repaired. And there are lots of other projects going on that try to make progress in research in medicine or in chemistry or in math. And if you're interested in that and you want to participate in computing, there are projects where you actually can do that with your own hardware. Now, I could talk about the characteristics of n-body methods, but then again, I don't want to spoil the assignment of this week, so we're not going to do that, and we're going to skip that for next week. And also, I could talk about optimizations of n-body methods, but then again, I don't want to spoil this week's assignment. So we are going to talk about that probably at length in the Proseminar, and I don't want to give anything away, so this is why those slides are not part of this lecture set. They will be added later on. Moving again to something else that we already know, structured grids. So for structured grids, I'm having a lot of sun in my lower face apparently. For structured grids, we model interactions between discrete fixed points where we have a grid structure that describes a pattern where these points are and how the topology looks like. And that should be enough, I guess. And this topological information is easily derived. So we have some kind of pattern, some kind of description of how to arrive at our topology. And on the right, for example, we see a cube, which is easily described. So whoever you talk to, even if they don't know anything about domain decomposition or HPC or something, it's really easy to describe this kind of pattern, right? This is very simple. The spatial locality is rather high normally, so we have these cubes which represent densely populated data structure. Every cube or every grid cell has a property that we want to deal with. In our heat stencil, for example, we saw that except for the optimization that Alex showed us, in the beginning we only compute on a reduced rectangle of our data, but still within this rectangle all the elements are concerned. And you can even use adaptive grids. I think I already mentioned them in a past lecture, where you can subdivide certain cells into smaller cells if you want to split up the computational load. But this doesn't make this approach unstructured. This is still a structured grid because, again, it's a really easy pattern that just says I have this cube, I can subdivide it into 8 additional cubes, for example, that are half the length each. This is still regular. This is still a simple pattern. You can write this down in a single sentence, right? And examples for these kind of problems are the heat transfer stencil that we did already, or basically any kind of problem in CFD, in computational fluid dynamics, or octrees, for example, where we try to, or quadtrees, where we try to subdivide our data structure into smaller, smaller compositions. Now, what are the characteristics of these? The structured nature of these problems is really a key aspect. So it's really good for these problems to be structured, because that helps us a lot. The characteristics of those are similar to dense linear algebra, for example. So I already said for dense linear algebra, they are similar to structured grids, while structured grids are similar to dense linear algebra, of course. You have issues like row major or column major access, or you have the thing that data resides contiguously in memory, which is good. This makes memory addresses, for example, predictable. So in hardware, you have memory prefetching units that try to predict. I think I already talked about this a little bit, but let's iterate it again. Hardware prefetching means you have a hardware unit in your CPU that tries to predict memory addresses, and once it figures out that you're always selecting every second element or every third element or something like that, it will prefetch this data before you ask for it with a load instruction. With the advantage that once you actually issue the load instruction, you do not have to wait for the latency for the data to arrive from main memory, but you only have to wait for the latency for the data to arrive from the level 1 cache, for example, or the level 2 cache, which is much faster. But in order for this to be predictable, you need to have some kind of structured system. So if I randomly select memory addresses, random is not really a pattern that can be grasped by the CPU. It's really hard for the CPU to figure out which element is he or she gonna look for next time. But for structured grids, this is really simple. So every next element, every second next element, or even if you do approaches like every second, every third, every second, every third, CPUs can figure that out, and CPUs will do prefetching. They are very smart these days. And as I also mentioned, adaptive grids are possible. So even with the structured nature, you still can subdivide into smaller elements. Now, usually, as I already mentioned, also with linear algebra, these problems are memory bound if you implement them in a naive way. Consider, for example, our 3D stencil, where we have 7 points that we use to derive the value of our center point. What you do is you load 7 data points for computing a single new data point. That's a lot of data loading, and then you store a single value, and very little communication, very little computation going on for that. So that's why these are usually memory bound, unless you can figure out a better way of iterating through your data using tiling or blocking, for example, or figuring out a different way your heat stencil algorithm works. On the upside, it only requires local communication or local data exchange, because the only data exchange you do is exchanging the ghost cells with your direct neighbor. Whether it's in 1D or 2D or 3D, you might increase the amount of data to be transferred, but still you only talk to neighboring cores or neighboring threads or ranks, whatever we are talking about. There's no global communication involved. You don't need any collectives for doing that. Overall, it's still important to know that structured grids doesn't imply rectangular, which is a mistake that people often make when they just quickly think about stuff, because we often deal with rectangular problems, like our heat stencil. But consider the figures on the right. We have a triangular grid, for example, or we have a hexagonal grid, and both of these are still structured. It's very easy to come up with a short description of how to assemble something like this. Just put triangles on top of each other and fill in the holes with triangles turned upside down. Very simple. Or the hexagonal pattern is just the same. These are also structured grids, they're just not rectangular. So you could also have problems that require you to fit something like this into some kind of array storage in your system and work with a representation that looks like this rather than a rectangular grid, for whatever reason. Now, what are the optimizations that we can do here? Well, as we talked about in the last lecture, it's really all about decomposition. It's the most important thing here. Remember the difference between decomposing a 3D structure into slabs or poles or cubes, for example, which has varying effects on the amount of data you need to exchange, and whether this amount of data decreases depending on how many processing entities are involved. And This really highly depends on the type of grid that you have, so the dimensionality or whether it's rectangular or not, and your specific use case, so how you access the data and how much data you need. On the right, I showed a simple visualization here again of the stencil where we have a center value and we need the neighboring values top, bottom, left, right, and front and back. And what's really handy for this kind of problems is that because they are structured, for a part or for a subgroup or a subset of these problems, we can actually have analytical prediction that sort of tries to derive performance characteristics of this code, because the code is so structured. Consider a 1D stencil. It's really easy to say, okay, I need to have for the center element the left and the right, a computer center, then I move one to the right, I do the same computation, then I do the same computation. This is so simple and so structured that you can have a performance model or a simulator built for that will try to figure out, for example, what is the number of level 1 cache misses when you execute this code on a specific hardware. What is the number of level 2 or level 3 cache misses? There's, for example, a tool out there, I think coming from the University of Erlangen and the Friedrich-Alexander University, Erlangen-Nürnberg, and it's called Currentcraft. And the thing with these tools are that these tools are really complicated in order to derive performance models for really simple input. So if you have a picture perfect stencil that you would find in a teaching example or a teaching book, for example, it will probably work and it will derive values that are fairly accurate. If your loops are no longer perfectly nested, if your stencil is doing something really strange by looking like this, but then taking one element that's 7 elements to the right for whatever reason, these tools start to piece by piece drop out because they can't deal any longer with your special algorithm, because it no longer fits this extremely simplistic description. So there's lots of research going on there, because performance models and performance simulators are something that is extremely interesting. It would be really nice to know the execution time of a program without running it, or even simulating it, but the simulation is much faster than actually running the program itself. People have been trying to do that for 20 or 30 years now. Performance models probably even longer than that, and this would be extremely useful in order to speed up development process, in order to speed up performance debugging of your program. I will have a lecture on that in a few weeks, but there's really nothing that helps you if you have an arbitrary C program, for example, because that would be sort of solving the Turing problem, the halting problem, right? If I know when my application is going to stop without running it, I solved the holy grail of computer science. So, but there are some simple tools that can help you with very simplistic type of programs. Now, compared to structured grids, we also have unstructured grids. I already hinted at that a little bit with my MPI lecture, where I told you that we do not only have Cartesian topologies, but also unstructured topologies, arbitrary grids. And this is what they look like. I think it's even exactly the same drawing that I used. So they are not described by a pattern, but rather by really enumerating, for example, the individual cells that we have and the individual connections, because there's no real pattern to come up with. In this case, you see they are arbitrarily connected. Even some cells that are fairly close to each other, like these two, for example, there's no connection in between, but then again there's a connection to the next one. Why is this the case? No idea, but this is the point of unstructured grids. We really need a description of all the connections. Usually it's just an enumeration. There's no pattern or short description that will allow you to arrive at a figure like this. And usually when you work with these kinds of grids, this involves multiple levels of indirection, because you cannot just have your array progressing to the next element where you say I add 1 to the index and then I'm at my neighboring cell. No, you need to ask the neighboring cell which neighbors do you have, and of these neighbors I select number 3, for example, and then arrive at the cell right next to it. These problems are highly used for computational fluid dynamics, and this might seem complicated. Why do people do that? And for that I have an illustration on the right, on the next slide, which shows you I think it's a fictional plane, I don't think it's a real plane, coming from a company, Numeka, which we worked with in our all-scale project, and they do computational fluid dynamics simulation when it comes to airplane turbines, for example, engines, when it comes to airplane wings or the landing gear and so on. And they try to simulate airflow, pressure, temperature and so on in order to design those things to be as efficient as possible in terms of flying, so have as little turbulence where you don't want it, because that slows you down, that drags the airplane. And to be as cost efficient as possible, because you don't want to design an airplane that's extremely efficient at flying, but it costs 5 billion for every airplane to be built. That doesn't help you, right? So why do we need unstructured grids for this kind of problem? You could also use a structured grid, but as you can see, the shape of the engine and the shape of the wing and the shape of the fuselage here doesn't really fit any structured approach. This is sort of cylindrical, this is sort of like a flat area, and this is sort of something in between, because it has the engine mount here, which is sort of flat, and then you have the engine casing itself, which is sort of round. It's cylindrical, but it has a hole inside where the air moves through. So using a structured grid for that doesn't really help you, especially because you could come up with a 3D grid going through over the entire volume of this airplane, and you simply omit everything that is not airplane, right? You omit all the points where you have free air, like around here, for example, and you're only interested in these points. But in order to arrive at a very accurate simulation, you need to have very small grid cells, and you need to have very small grid cells at locations where you want them and not at locations where you do not want them. For example, if you take a look at the fuselage here, you have very large grid cells because there's sort of laminar flow going on here. There's very little turbulence, so you don't need any high accuracy. You don't want to spend lots of computational power here. And as soon as we start to move away from the simple geometric structures to more complicated ones, like here, where the wing is connected, we need to start to increase the accuracy of our simulation. We need to start to decrease the size of our cells, because that's where turbulence happens, and that's where the math gets more complicated. So we need to spend more computational effort, and we need to spread out among more ranks or threads or whatever you have. And this is also why you see, for example, a finer grid here at the front of our engine compared to the center section of the engine, because there's lots of interesting turbulence going on here, but very little turbulence here. And the same applies for the wing. And this is why you use unstructured grids, because you really want to map this geometrical property, the shape of the engine, and you want to do this with as little computational expense as possible, and structured grids are simply not suited for that. And it can get even worse than that. You could have a simulation, for example, consider the engine, where you have the turbine inside that is actually has rotating blades. You could have a grid that is rotating while you're doing your simulation. So part of your grid is stationary, part of the grid is rotating inside, and you need to incorporate both of those into your single simulation, which is a really, really complicated thing to do. But that's what companies do in order to, for example, design engines that are 3% more fuel efficient. That's really what happens in real world. That's why it's so expensive to design and build new airplanes. So I told you on the previous slide, this is heavily latency bound because you need to traverse your structure. And this is what it looks like with those code examples. You could, for example, have an array of cells and another array of neighbors that identifies for each cell what's the index of a neighbor. So I would be the index of a cell, then I check the neighboring array, what are the neighbors of this cell at some certain position, and then I access the actual cell using this index. And that's indirect accessing. That's something really bad, because this could potentially lead to random access. It's not just every cell after the other consecutively that you are accessing, but depending on the content of the neighboring array, this could look like random access, for example. And random access is always latency bound, because you will access elements that are not in the cache, or with a high probability not in the cache. And you could also write this differently. You could use a C++ structure, for example, with a member function, getNeighbor, and this simply accesses some internal array or vector, but it doesn't really matter why you write it this way or this way. This might just be hiding the access in some syntactic sugar in order to allow you to write this in a more high-level or more fashionable code. But the thing that happens is the same. Essentially what you're doing is pointer chasing. You have like a linked list, a certain cell, you ask what's the neighbor, you might ask even the next one what's the neighbor, and then you only access the data for this one, and you probably have, with accessing one pointer, accessing another pointer, twice the latency of going to main memory because the data was not in the cache, compared to accessing adjacent elements. And the problems that you deal with here are very similar to structured grids, just a lot more complicated. But essentially they're still the same. So you still have the problem of domain decomposition. You have the problem of adaptive grids where you try to subdivide your domain into smaller elements. But then again, how do you do it? For example, you see here that part of this data is only divided vertically but not horizontally. And you end up with non-rectangle or non-quadratic shaped cells. So this is one thing. Then again, topological information. How do I actually connect the individual cells? We're gonna have a slide on the next slide on that. The ghost cell exchange. Of course, you need a ghost cell exchange if you want to do a heat stencil across this. But how do you implement this if you have cells that are of different size, for example? It's still sort of the same thing. Consider that your regular structured grid stencil is just a special case of this one. You have a heat stencil where every neighboring cell has the same size. If you do not, if you no longer have this constraint, you end up with an unstructured grid, for example. And this is really what people do, but this is hardly analytically predictable. So there's no way of doing this because the problem formulation is so complicated that you simply have to implement it out and run it and see what happens rather than trying to analytically predict what's going on. You just can take some intermediate reasoning. Okay, that's how many cells I usually access before I arrive at the value that I need for my computation, and that's how many pointers I need to chase before I arrive at this value, and so on. But these are really statistical approaches. There's nothing analytical that will arrive at the fixed value that actually holds for your program. So what kind of optimizations can we do here? Well, as I said, with it's sort of similar to structured grids, and it's all about discretization and topology, but it's more complicated than you might think. It's not only about where are the elements, but also what type of elements do I have. So on the top right, you see what an unstructured grid could look like, or these are also sometimes called unstructured mesh, which is just a synonym. We have elements, for example, that are cubes, A, B, C, D, and E, and we have faces in between that are enumerated 1, 2, 3, and 4. And A is not directly connected to B. They are not direct neighbors, but rather A has the neighboring cell 1, which is of a different type, and the other neighboring cell of 1 is B, which is again not a face type, but it's a cell type or a cube type. And in implementation, this would look like this, that you have a pointer going from A to 1, and a pointer going from the face 1 to your cell B, for example. And if you want to move from A to B in order to figure out what's going on at B, you need to move through this chain of data structures. And this could be more complicated. You could have the individual vertices as separate data elements. You could have the edges as separate data structures. And you have various ways of connecting them, for example, where it might make sense to have the vertex here connected to the faces, or maybe only to the cells and not directly to the faces. This really depends on how you exchange data, whether you want, for example, air to move through a face, where you want to compute the energy flux that is going from B to A or A to B, and so on. This makes these programs really complicated, and for whatever you choose, you have to consider that this needs to be efficient when loading or storing the data, not only to main memory, but also on disk, for example, because you need to load your input data at some point and you need to store your result data. Then you need to be able to navigate it efficiently, and then you need to be able to do computation efficiently. So this is a really, really complex problem, and this is why it costs a lot of money to do proper implementation of these kinds of problems. And yeah, I said, as with structured grids, decomposition is the most important thing. This also holds for unstructured grids. You need to do proper decomposition. You need to implement an efficient, or be able to implement an efficient ghost cell exchange, and do efficient navigation. For example, on the right, you see this unstructured grid where I have, for example, my center cell, and let's say I want to do a heat stencil. I want to compute all the neighboring cells that are in a certain range. The problem with that is, if I choose the direct connections here, I get these cells that are sort of in hatched color here, orange and blue, but this cell is also in range, but it's not a direct neighbor, so it's not included. Now it depends on your algorithm. If you're only going for the direct neighbors, you're only going for the neighbors as defined by your topology, then this is perfectly fine. If you're going for neighboring cells measured by distance, you need to figure out an efficient way of determining which neighbors are close to me, and this could be expensive. You could go, for example, for every neighbor of the neighbor of the neighbor, then for all of those, compute their position in 3D space, compute the distance to the center cell, and then figure out if they should be included or not. And you might miss a few cells because you don't know how many neighbor connections you need to progress through, because you could have very long or very short connections depending on your geometry. Or it could be that you're navigating through way too many cells because you want to be very, very sure and very conservative, and you're spending much computational load on navigation and computation, and just arrive at very few cells finally that you select, and in the beginning you traverse through many more cells that you actually were not interested in, but you didn't know before because the geometric structure is not represented in your topology. So this is something really complicated. This really depends on your use case, your data structure, the problem that you work with, and yeah, takes years of research to do this properly. Lastly, for the dwarfs that were initially established, the initial 7 dwarfs, we have Monte Carlo methods, and again, this is something that you know. These methods are sometimes also called MapReduce, because what it means is to process data independently, sequentially potentially, and merge afterwards the results. And this is why they're really nice, because they're also so-called embarrassingly parallel. It's really easy to come up with a parallelization scheme, just individual multiple samples, do all of them individually at the same time, and at the end we have a single reduction operation, and that's it. They scale really well usually, as long as the individual sample evaluation can be done independently of each other, and if it takes a sort of minimum amount of time, but usually this is not a problem. And what these represent in real world is statistical evaluation of random trials. In our case, it was just selecting points in a 2D domain and checking whether they're inside a circle or not in order to arrive at the computation of pi. Computation is insignificant because there's no exchange, and this statistical evaluation also happens in other problems out there in the real world. Every time you try to do a statistical sampling, did this happen or did this not happen? If I change the parameters, did it now happen or did it not happen? And you do this for 1 billion times, and then at the end you do some kind of counting or averaging or what have you. And these methods are used mainly in numerical integration, like we used for the computation of pi, or approximation of pi rather, because you can't compute it, of course. There's the quantum many-body group of problems which use this, which deal with interactions of individual particles. There's ray tracing, for example, which is also embarrassingly parallel, because first you cast some rays that simply progress through a domain, and you try to see where they reflect, where they refract, and so on. And at the end, you have a reduction which simply assembles all the pictures, all the pixels in your picture. So that's also ray tracing for you. What are the characteristics? Well, I've already mentioned that, and it's quite fast because we did it in the Proseminar. Parallelization is almost a no factor because there's very little overhead. Basically, it's the same as running multiple sequential programs. The only thing you have to worry about that they share some resources. For Pi, the cache was not really that important. I mentioned it as an example here because why? Well, we didn't work on a lot of data really, right? We have a few double precision floating point numbers. We have a few integers, and that's everything we deal with. That's no memory footprint whatsoever. That fits in a few registers. We do have a shared resource, for example, the random number generator. If you didn't switch to a random number generator that is reentrant, or if you actually use a reentrant random number generator that, however, uses locking, because you could also just make a critical region, then you have a shared resource, and then, of course, it's no longer running just individual independent sequential programs because you have resource contention. Other than that, the reduction at the end is usually quite inexpensive, and the only thing you really can do here is optimize the sequential code as much as possible. So choose a fast random number generator, try to do lots of ILP optimization where you, for example, try to hand code assembly if you want to be faster than whatever your compiler is pushing out. Try to do prefetching if you actually do work on data. For Pi it wouldn't help because we don't. What you could do for Pi, for example, is vectorization. You could try to implement a random number generator that computes random numbers, multiple of them at the same time, using vector instructions in the CPU, and compute 4 numbers at the same time instead of just 1. Or you could have this evaluation whether points are inside or outside of the circle, also using vectorization. This is something that probably would give you some speed up because you're heavily computationally bound because there's no data that you work with. And other than that, try to minimize the resource contention. In our case, for Pi, for example, that means use a really fast random number generator that still fits the random number qualities that you need for your math that you're using. Beyond code optimizations, what you could do is you could consider using different hardware. For example, ray tracing or rasterizing images in computer games. Use GPUs for that. GPUs are well suited for doing very simplistic but sequential tasks where you do not have a lot of global communication going on. GPUs are perfectly suited for that. That's how they are designed. You could use FPGAs, for example, where you wire the FPGA in such a way that is perfectly capable of implementing your algorithm, sequentially evaluating what's going on in your sort of makeshift transistors, and only afterwards you do global communication and aggregate all the data. And whatever you do, try to decrease the computational cost, whatever that means, time or energy or whatever, of evaluating a single sample. And you could also consider, for example, decreasing the cost of a single sample and making it less robust, so making it less accurate, but increasing the number of samples then. If you can come up with a random number generator that is less suitable for whatever you want to do, but it decreases the evaluation time by a factor of 10, and you only need twice or 3 times the number of samples to mitigate that, you still end up with an overall performance improvement. And you could try to increase the number of samples and make each sample less accurate but faster to compute, depending on your problem. Beyond that, there's really not that much you can do with Monte Carlo methods, beyond the math that is involved, because there's very little entities involved, there's very little memory hierarchy. There's not that much you can do. Now, those were the first 7 dwarfs that people came up with, and I already told you that these sort of represent processes that are happening in our real world, in our physical world. You try to simulate things, you try to see what's going on if a river flows down a country, if you have waves crashing on the ocean, if you have avalanches going down the mountain, and so on. All of this stuff, car crash simulations, all of these are really simulations or models of physical processes. But that's not the only thing we can do. We can, of course, also do something like combinational logic, for example, where we want to figure out how many solutions there are to a certain problem. We could have graph traversal, for example. We can have dynamic programming. I will give examples for each of those. Backtrack, branch and bound, where you try to figure out a certain solution, and if you figure out that in a tree structure you do not have any possible means of getting to an acceptable solution, then simply cut this subtree and do backtracking to the last state that still worked. Graphical models and finite state machines. I will present all of those now, but in a sort of more dense context by just having a single slide of all of them, presenting you with examples and arguing a little bit about what can be done and cannot be done. And many of them focus more on integer-heavy applications and a little bit machine learning, for example, and less on physical processes, but that's not overall true. So that's just the general direction that these take, which is why I think they were added on later on, because people first started with the physical processes that we can see and experiment on in real life, and these are more like theoretical problems. But that's not exclusive, obviously, so you can have outliers. Let's first start with computational logic. So combinational logic generally involves doing operations on lots of integer data. An example that I showed on the right here is computing checksum, for example. Could be CRC 32 or what have you, Adler 16 or whatever redundancy checks are out there used for Bluetooth and I don't know what, where you just do a lot of bitwise operations, shifting, for example, accessing arrays, but at really short arrays at certain positions, like my first byte or my 8th byte or something, and all of this data is usually segregated into individual blocks for encryption, for example, and all of these computations are really heavy on doing bitwise operations, like doing bitwise AND operations or doing bit shifts and so on. There's no real global communication going on. You don't progress beyond a certain block size and so on. And how do we deal with that? They are often parallelizable on multiple levels. You could do bit level parallelism, or you could do block level parallelism. So block level parallelism means if I chunk my data already to be individually encrypted or to have individual checksums computed for those, well, then I just compute the checksum for multiple blocks at the same time. They should be independent anyway, right? or bit level parallelism, I can come up with instructions that parallelize this operation over several bits. I do not, if I want to check for every bit, for example, whether it's set or not, I do not need to do shifting and do logical AND operation for every single bit in an integer. I do have instructions in x86 that allow me to do this kind of operations over the entire register at once. For example, x86 has an instruction called pop count, which computes how many bits are set in a register. So you could have an integer with the value 3, for example, where you have the two least significant bits set, the bit for 1 and the bit for 2, right? Binary representation. And if you do a pop count on this register, it will tell you 2, because there are 2 bits set for your register. Computing this yourself would take many more instructions. You could even do something really bad by storing individual bits as a bool vector or a bool standard array, for example, in C++, and then do operations on that, all of which might be much less efficient compared to one x86 instruction that can work on 64 bits at the same time and in a single clock cycle tell you how many bits are set. This is how you optimize these kinds of codes. So it's really low-level stuff. The next dwarf is graph traversal, which basically consists of traversing, well, a graph, which is a number of objects. On the right side, I showed you an example, which is a tree structure, where every element has the same number of children, which doesn't necessarily have to be the case. And you examine certain characteristics, and you do that, for example, in applications like searching or sorting. You did a ton of those, I guess, in algorithms and data structures in the bachelor. It could be collision detection in a game, for example, whether you want to make sure that people do not run through a car or through a tree or through the wall of a building. It could also be decision trees where you try to figure out what you should do, for example. And these kind of problems and data structures are usually very heavy on reading data and looking up data, fast navigation through your graph, for example, but there's very little computation going on most of the time, and there's very little output or writing. So usually, if you have sorting algorithms, you modify the tree a lot, but for collision detection and searching, there's very little modification going on in the tree, because you do lots of reading, lots of checking and lookups, and this also touches on what I told you. When you design data structures, be aware of the kind of operations you need. So whether you use a set or a vector or a map or something, consider first what is the type of operations that I need and how often do these operations occur. And if I have a data structure that is doing 1,000,000 reads for a single write operation, that a single write operation can be really expensive probably, because you don't care about it. You want the 1,000,000 read operations to be really fast. That's why we have different data structures. And this could be parallelizable, for example, over different paths in the graph. So this could be serialized into an array, for example. This could be implemented with pointers as sort of like a linked list. Really depends on what you need. However, if you do something like the latter, like doing linking with pointers and so on, be aware that, as again, if you have indirect accesses, this is usually heavily latency bound, because you end up with pointer chasing in order to go from this node in the graph to this node, to this node, to this node, and finally having the data or the decision that you wanted in the end. So depends on your use case. Then dynamic programming, which is basically a group of problems that try to solve solutions by computing simpler subproblems. Some of you might know the picture or the example on the right, for those of you who did the OpenCL course in the bachelor, which is matrix chain multiplication. So you have the problem, you want to multiply several matrices A times B times C times D times X. And with the law of associativity, you have multiple ways in what order you can do these operations, and doesn't matter which order you choose here, the end result X will always be the same. So obviously this holds, otherwise matrix multiplication wouldn't be associative. However, it depends on the grouping of your operation, and hence the order of operations, how you do those. You end up with different number of operations. So for example, if I count the individual multiplication operations that I have to do, or the individual floating point operations, if I come up with this order, first doing C times D, then I multiply B with the result, and then multiply A with the result, I end up with 154 operations. If I choose this mapping by first computing A times B, computing the result times C, and then again computing the result times D, I end up with more than twice the number of operations, while still computing exactly the same result. So obviously the order here is really important. And how can we use this knowledge? How can we optimize this? Well, we have common subproblems here. If we take the first and the second variant, for example, for both of them, we first multiply C and D, and we can reuse the knowledge of how expensive is C times D when we compute the second variant. Or for example, the same appears in the second variant and the third variant. Both multiply A and B first before they do anything else. We again can use this knowledge. And we don't need to recompute for the third variant how expensive is A times B. We already did in the past. We just need to have a data structure that allows us to store this kind of information and reuse it later on. And this is what people like to call memoization. So you try to come up with a data structure that allows you to save intermediate results and that allows you to memorize a subproblem that I already solved. So next time I come up with the same input parameters for this subproblem, I do not need to recompute it. I just look up what was the result and use it. Sometimes people also call this caching. You sometimes have this with lookup tables, for example. So in certain problems, for example, heavy integer division, it might be more useful to have a lookup table and store various results of integer division operations and not do the actual computation, but simply check, okay, I'm dividing 7,971 by 153. What's the result? Instead of doing the computation, I just look up both parameters in my result table where I store all the results that are possible and then simply use the result. It will require a lot of data, but it might be faster than doing the actual computation. Depends on how expensive they are. And these kind of dynamic programming problems just all relate to something where your overall solution is compared of sub-solutions, and you can compute the overall problem by a series of sub-problems that you do not want to recompute every time they appear in your sort of tree. The next dwarf we want to talk about are backtrack and branch and bound. So these are search and optimization problems for very large problem spaces, where you try to incrementally build a solution, and once you try with your incremental approach and you arrive at a point where you figure out, okay, I'm now at a point where I can no longer satisfy the constraints, I will never arrive at a correct solution with the current path that I took, then I simply disregard that, move back, do my backtracking, so to speak, and try a different route. Reusing everything I computed so far, but omitting everything that I just saw leads to a wrong path. A popular example here is the n-queens problem, which just means given a chessboard of 8 by 8, so this would be an 8 queens problem, I try to place 8 queens on this chessboard such that no queen can attack any other queen. You do this now, for example, there are a ton of ways of solving this problem. This has been well studied in literature already, and people try to work on this still. You could place the first queen and then figure out, okay, I need to place the next queen in another column, so which column do I choose? If I choose the B column here and I choose the row 2, those two can attack each other. So it doesn't matter where any of the remaining 6 queens will be placed. This is definitely not gonna satisfy my requirements. So a solution that has 2 queens on the same row or on the same column, I can already omit from all my solutions. Which means if I attempted to place my queen here, I do backtracking and say I'm not gonna do that. Instead, I'm gonna place my queen here. Is this possible? Yes. Okay, so I can progress further and try to deal with third queen, for example. And as soon as you enter a state where your constraint is no longer satisfied, the constraint being that queens cannot attack each other, you simply move back and try to vary a little bit. And this can be computed for various numbers of queens. So in the example on the right, you see the 8 queen problem. And this, due to the exponential growth of the potential solutions, the computational expense for this is really large. So 10 queens problem, for example, you can solve an LCC2 probably, or an 12 queens problem. If I want to have you compute a 30 queens problem, this will never finish because of the exponential explosion of the computational intensity. And the type of solutions you use for this is a divide and conquer strategy. So you try to break it down into smaller subproblems similar to the draft that we had before. In this case, for example, we place a single queen in the grid cell 1A or A1, for example, and we try the different solutions, but then again in parallel we could try to compute what happens when we place the queen at A2, A3 and A4 and evaluate those branches at the same time. So this is a problem where you could use nested parallelism, for example. and try to speed up the overall computation like that. Then there are graphical models, which are also known as probabilistic models, and they just consist of some representation of random variables and dependencies that you use for making decisions, for example, like Bayesian networks or hidden Markov models. So the example on the right I chose, which I altered compared to last year, say your mood depends on both the weather and COVID-19 news that you just saw on TV or read on the internet. Last year this used to be the quality of Mensa food, but since nobody's going to Mensa these days, at least students are not, I changed it to COVID-19. And this has an impact because, for example, if it's sunny or if it's rainy, then this has an impact of 0.4 probability or 0.6 probability, and COVID-19 has a probability of 0.9 and 0.1, for example. And then you can come up with your overall table that decides whether you're in a good mood or in a bad mood, depending on whether it was sunny and whether the COVID-19 news was good because we had a decreasing number of fatalities, for example, or whether it was raining and you saw on TV that lots of people died from COVID-19. So this is sort of like a graphical model that is used in math. Bayesian networks and hidden Markov models are just two examples. And there's really ongoing research in math and computer science how to optimize and parallelize them properly, depending on what the structure of your model looks like and so on. And I'm not going to go into too much detail because I'm not dealing a lot with those. And the last dwarf we're going to talk about before we're going to move to Tales of the Proseminar, for which we have just enough time, I hope, is finite state machines, which represent an interconnected state, a set of states that you can move along. So on the right, for example, we have a start state with a start operation through which we arrive at state 1. Then we do creation of something. This could be, for example, kicking off a process in your operating system. Afterwards, you might have some synchronization or initialization going on, some replication, whatever. It doesn't really matter what the finite state graph here represents, but just to give you an idea of what these finite state machines look like, I think you already did some in some computational logic subjects or courses. Another example would be ParSys, for example. By parsing C or C++ language, you can use a finite state machine to derive at different states. So I have a declaration. If it's a declaration, then I need to have a data type, for example. If it's declaration and initialization, there needs to be a value that follows, and so on and so on. And people also try to do research here. Those are not very well researched in terms of parallelizing, because if it were, we would have parallel compilers, for example, that could compile a single translation unit or even a single function in parallel, speeding up the process. But people try to find ways of decomposing these state machines into multiple ones that you can evaluate at the same time and try to derive the final result in a faster way. But this is still ongoing research. Okay. If you want to read up more on those, again, the link of all those dwarfs, which with additional descriptions, with additional visualizations of the communication and data exchange patterns, and also some related aspects. I think it's like 18 or 20 pages long, if I remember correctly, and it's quite a nice read if you are interested in these topics. However, what should be always considered is that I showed you now several examples of dwarfs, how to classify HPC programs, but this is not the only thing, for example, you can do with MPI or OpenMP. This is all simulating something in theory, computational logic, graph models and so on, or physical processes like our heat stencil or moving particles. All of this is something that really relates to another branch of science that is not computer science. However, you could also just use MPI, for example, to implement a runtime system. You could implement an operating system that runs on multiple nodes at the same time, and you do communication via MPI. That's also science, it's just computer science, it's not math or physics. You could, for example, try to emulate shared memory systems on distributed memory using MPI by implicitly moving data around as soon as somebody accesses the data, which is the point of PGA systems, which stands for Partitioned Global Address Space. So there are lots of systems that I will show in a later lecture that try to emulate shared memory. You just access data without any message passing, and as soon as you access the data is transferred in the backend without you having to write a send or receive method. And in general, MPI, for example, can just be used as the connecting layer for connecting shared memory systems or connecting sequential systems. So what we did at University of Innsbruck, I already mentioned it, is the Celerity project, where we try to write programs that use multiple GPUs or multiple accelerators on separate nodes, and the user doesn't have to write a single send or a single receive method call. Or you just want to implement something that extends shared memory parallelism, like you have a special FPGA GPU, you want to use OpenMP or SYCL or something special, and you want to extend it to distributed memory parallelism, then you do this MPI plus X approach. So whatever you have, you add MPI to deal over the network. And still, it should be said that the majority of codes out there that you will find that are implemented using OpenMP or implemented using MPI, they are still scientific computing codes that deal with physics problems or chemistry or medicine or whatever, and they are not focused on computer science, because computer science usually just uses, I don't know, TCP sockets or UDP or whatever you use. But it could be used also for that. There's no reason, there's nothing that prevents you from doing that. Now, moving to the next topic, and afterwards I will open for question in case there are any questions. Tales from the Proseminar. First, I will focus on Daniel's weird integer problem, and afterwards our GCC versus G++ compilation. So Daniel, you don't know him, but he had a very interesting thing happening, which I didn't understand in the beginning. Daniel had a sequential 2D stencil, just like you implemented it, and he ran it with a problem size of 100 by 100, so comparatively small. Ran it without optimizations, but you could also enable optimizations. The same thing will still happen. We tried with GCC 4.8, we compiled with 9.2, we even tried it with Microsoft Visual Studio. Whatever you do, if you switch loop iterator variables, so the loop iterator variables for I and j that determine where in your physical domain you are, and you change them from long type to int type, it halves the execution time. So the stencil took half as long. On the right side, you see actual measurements that I took on LCC2. Using the time command and just going for the elapsed time and not the entire output. For the version with the long data type, it took 4.6 seconds. For the version with integer, with 32-bit integers, it took 2.3 seconds. And okay, of course, I mean, long is a 64-bit integer. It's twice the size of a normal int. But then again, in increment and everything, integer operations, these simple integer operations like checking whether we exceeded some boundary or incrementing it by 1, those are single clock cycle operations. They shouldn't take any longer on a native 64-bit architecture that has provisions for 64-bit integers, right? We don't care about the pointer length. I had no idea why the heck this was slower or faster. I would expect there to be a performance difference of a few percent maybe, but not a factor of 2. So let's try to see what's going on. We profiled this with gprof, which is a tool that we're going to discuss even further in later proseminars. It does profiling of codes and tries to check which parts of your code make up how much time of your overall execution time. And so to speak, it finds the hotspots. So which parts of the program are the most computational heavy. And we figured out that okay, we have 3 functions that make up most of the computational time, and they are all the same, or not 3 functions, but rather 3 lines of code, and they are the same. So here we have lines 93, 78, and 79, and here we also have 93, 79, 78, but they are in a different order. So line 93 takes 0.75 seconds for the right case, which is long, and the left case is int, which is 76 seconds, so that's almost the same. There's very little difference. But lines 78 and 79 here take 1.5 seconds and 1.7 seconds, and here they just take 0.5 and 0.3 seconds, which is much shorter. So what the hell is going on? What do those lines actually look like? Here is the code that Daniel wrote, or rather an excerpt, which had lines 78, 79, and 93. For line 93, we see that this is the actual computation going on. And we don't care much about that because it's just a computational operation, and we saw between int and flow and long there was no difference. There was very little difference, which is just noise probably. The large difference actually came from those operations. So what we do here is we try to compute the value of the left neighbor and the right neighbor, and we try to do boundary checks. If we are not at the boundary, we take the neighboring value, otherwise we take the center value. And this is a two-dimensional stencil. However, Daniel's group implemented this as a single-dimensional problem. So instead of just checking for larger or smaller or something, they need to use the modulo operator. So I saw this code and I figured out, okay, we use the ternary operator here, which is just like an if-else. So maybe the branch prediction in the CPU is really bad and it ends up branch predicting this wrongly. So the CPU thinks we're always going to go for the center value, but we have lots of evaluations that end up with the neighbor value. In order to figure that out, I ran the perfstat tool and I tried to look at the number of branches that were taken and also the number of branch misses. Again, the left is integer, the right is long, and the problem is there was no difference. So if you look at the numbers, the number of branches is 1.2 billion for integers and 1.2 billion for long, which is exactly what I expected. What I did not expect is that the number of misses that were mispredicted was approximately the same. It was about 1 million for the integer case, also about 1 million for the long case, and still we arrive at the execution time of 4.6 seconds for long and 2.3 seconds for integer. So this definitely was not the issue, and I was wrong. But that doesn't help us. What was actually the problem? So we actually looked at the generated assembly code and we found here what you see is the assembly code up here, the line that we had, line 79 or 78, I can't remember, doesn't matter, both of them have the same problem. And below here you have the assembly code that happens when you do this. And what we found is actually that we have a lot of operations that are sort of cheap. We have a move operation, and it's probably a single clock cycle, a test operation, a jump if equals. All of those are really fast. However, we have an integer division, and integer division, even though it's integer, a division is quite expensive. It's a quite complicated math operation to do. So we thought, okay, maybe let's check if the integer division is actually as fast for long compared to integer operations. And when we did that, well, oh surprise, we found information on Agnes Fogg blog, which is a guy, I think he's a researcher from a Danish university in Copenhagen or something like that. I linked the PDF here below for anybody who's interested. This PDF is a really nice reference document that holds latency numbers for instructions on various x86 architectures, including Intel Skylake, for example. And when we checked this, we checked for the integer division operation for 32 and 64-bit operands, and the latency is vastly different. So the latency for 32-bit is always 26 clock cycles, and for 64-bit it can vary between 42 and going up to 95, depending on the state of your CPU and depending on what the operands actually are, what the content of your data is. And this easily explains a factor of 2 difference. If you want to study something like this yourself, I can recommend Godbolt, the compiler explorer, which is really interesting and which can really help you with these kinds of things. And the root cause of the issues really was, so we figured out if you change that, you end up with an IDIF operation that's much faster, and this was actually the cause of our performance slowdown. The root cause, however, the high-level cause was that we had a single loop for a multi-dimensional problem space, because Daniel's team thought it might be faster, or simply came up with the first solution: let's start with a 1D representation and linearize the index ourselves. And if you do that, in order to compute the boundaries, you need to use the modulo operation, because you will have multiple I values that represent the boundary. Compared to 2D, where you either have one value for I or j, whether you're on the top or on the left, for example, or another value for I and j if you're on the right or on the bottom. You do not need to modulo with that. You can replace them with a loop nest, for example, and comparison operators like equals, not equals, or larger or smaller, or less than rather. And if you do that, you omit these expensive modulo operations, and just by changing from 1D to 2D and using those operators, your code will be faster. But not because of the index structure or something, just because of the way you identify whether you're at the border and need to implement the border condition. And this potentially violates the premature optimization thing that I talked about in my 4 steps to creating an optimized parallel program. Come up with the simplest solution, and I would argue that the simplest solution for a 2D heat stencil is actually a 2D representation in my code, but this is a subjective evaluation, I guess, so some of you might think that a 1D representation might be more straightforward. Who knows? But just to show you how weird stuff can get, and to be honest, I didn't know before that long integer divisions can be that expensive, or that much more expensive than 32-bit. But it was a really interesting teaching case. So that was Daniel's problem. And the second one is really, really fast. That's what we discussed yesterday, I think, where I argued that compiling G++ versus GCC for the same code that is a subset of both C and the C++ language will basically behave the same way. And you have to be careful with that, because not every C code is also valid C++. Just name a variable in C, name an integer variable class, for example. This is perfectly valid in C. If you compile it with G++, you will just get compiler errors. And this other way around, obviously, not every valid C++ code is valid C. But if you end up with a code, as you see on top here, which is valid in both language standards, you end up with assembly for G++ on the left and GCC on the right, which is not exactly the same, and I was really surprised. So the beginning of the entire move, where we save our stack pointer or our frame pointer, these are still the same, and also the returns and the no-ops down here are still the same. I compiled this without any optimizations, so that was O0. However, in between, it actually differs. So for the G++ case, what the compiler is doing, first issuing a compare, and then it checks whether the content is greater than a certain value. If yes, we jump to L2, which means we jump out of our loop. So it first checks whether it doesn't really check whether we want to stay inside the loop, it rather checks whether we want to move outside of the loop. And on the right side, we do it differently. What we first do is a jump to the L2 mark, which is comparing and then not jumping with a if greater, as you see with the JG here, but rather with a JLE, which means jump if less equals. And this is basically just a negation of this operation. So the semantics of both of these order of assembly instructions is the same. Of course, otherwise the compiler would be generating wrong code. Just in one case, it checks, should I stay inside the loop if the value is smaller, and on the other case, it checks, should I exit the loop if the value is larger, which is the same semantics, just doing it the other way around. And of course, compilers are free to do whatever they want as long as they end up with a semantically correct program, which is the case here. But I still found it interesting that just switching the language standard causes GCC's internals to end up with probably different intermediate representations that end up with this different assembly code, which might have a little bit of a performance difference. It might not. Really depends on how often you call a loop like that and how expensive the individual operations are, but probably you will end up with the same performance anyway. But it's still interesting to see that the assembly output is actually different. Well, coming to a conclusion with a little bit, a lecture that's a little bit too long. Sorry for that. So we discussed the 13 dwarfs of HPC, which are just abstract application categories and more high level than just saying this is task parallelism or this is data parallelism. It allows us to reason about parallelism in a cross-platform, in a cross-application way, in order to design hardware. What should hardware look like that fits one pattern, or what should a performance model look like? What kind of optimizations do I want to apply, and so on. We discussed the 7 older ones that are mostly well-studied physics problems, and the 6 newer ones which are a little bit more theoretical and more subject to ongoing research. And they just try to give you a broad perspective on what's going on in HPC, what's the potential, what can I do, what kind of problems exist, and how are they limited, and how could I get around those limitations maybe. And afterwards, we discussed Tales from the Proseminar, which shows the weird integer problem, which means basically the takeaway here is don't consider integer operations to be cheap just because they're integers and not floating point numbers. And if you really want to know about the performance, you really need to dive into what instructions are used, and you need to read up on the latencies, which takes a lot of time for long codes. This is really difficult. But first of all, profile your code and try to figure out where are actually the slow portions of your code, which again means measure your code. Don't try to optimize without first profiling and checking what is actually the problem. Don't optimize on a hunch. Optimize based on measurements. And the second one was just from yesterday's Proseminar with GCC versus G++, where we see that the compiler is actually generating different code, although there's very little reason because the code example is very simplistic. But then again, compilers are very complicated entities, so it's free to do that as long as the semantics are still the same. With that, I conclude the lecture. Are there any more questions?